So I've got a couple problems to work through, talk about these exponential and logarithmic functions inside some real scenarios. So atmospheric pressure P in pounds per square inch is represented by this function here, where x is the number of miles above sea level. So what is the pressure at sea level? Well, if x is the number of miles above sea level and at sea level, that's the same thing as asking, what is it when x equals 0? Well, 14.7 e to the negative 0.21 times 0. That's just p to the 0. Or p of 0. So this becomes 0. We get 14.7 e to the 0. Any base to the power of 0 is just 1. That's going to be 14.7 pounds per square inch. And if I graph this function, you can see that at 0, we have 14.7 pounds per square inch. Notably, right, as the height above sea level, the number of miles above sea level increases, the atmospheric pressure decreases. Right, this is atmospheric pressure. So as you get higher and higher in the atmosphere, the pressure decreases. That should make sense. The lower you are, the more stuff is pushing down on you, so the more pressure you would have. Okay, to the nearest foot, how high is the peak of the mountain with atmospheric pressure 8.369 pounds per square inch? If p to the power of x equals 14.7 e to the negative 0.21x, we're asking how high is the peak if the atmospheric pressure is this many pounds per square inch. So if p of x is 3.69, because we have pounds per square inch, and that's what p of x is, then all we're asking is what is x at this value. So we're going to divide by 14.7. That's going to give us 0.5693 approximately, e to the negative 0.21. Now we're going to take the natural log of both sides to get rid of that e. That's going to give us 0.5633. And that's going to equal negative 0.21x. Then finally divide by that, and we'll get our answer. We get 2.6824 approximately. And this is miles above sea level. And it asks to the nearest foot, how high is the mountain? So this is 2.6824 miles. There's 5,280 feet in a mile. So that means that there's going to be times 5280. That's going to give us approximately 14,163 feet. That's how high the mountain is. And real quick, this is a y value of 8.369. A y value of 8.369. So we just go y equals 8.369. We can see here that it crosses right there, the graph, and that gives us an x value of 2.682, which is what I found, 2.682 for the x. So you can, of course, just use the graph to calculate this. You don't have to do the algebra, but just wanted to show you both ways. Okay, the sigmoid function, which is 1 over 1 plus e to the negative x, and its transformations, they model a lot of stuff. Probabilities and diminishing returns, I think, are the ones that I think of first, but they model also population things and a lot of things. So here we have a population for a species of wolves, and we have this population function. It's a transformed sigmoid function. X is in years. So we're going to graph it and show the population over a span of 10 years. So here's the function, graphing it. And so over a span of 10 years means that we're going to graph from 0 to 10. And of course, we don't care about zero population. It can't be anything like that. I'm just going to go 100 here and see if that's enough. That's not enough. I need more. Let's go. Okay, here I've graphed it to 500. So over a span of 10 years, it goes from a population of 10 all the way up to a population of 362. And you can see that actually it'll end up capping off at some point. This is what a typical sigmoid function looks like. It's this kind of S curve here. Okay, what was the initial population of the wolves transported to the habitat? Well, that's the same thing as x equal to 0. You plug in 0 there, you can find it, or we can just look on the graph. It says 0 was 10, so the initial was 10. Now, how many wolves will be the habitat after 3 years? Well, 3 years, plug 3 into there, calculate it all out if you want. We can also just look on this, on the graph here. And it says 3 is 37.9, so 38. 38. Now, how many years will it take before there are 100 wolves in the habitat? So 100 years, or sorry, 100 wolves is going to be right here. This is at 100. That corresponds to the year just about 5.37. Let's find it exact though. So I'm going to make y equal to 100 and find the point of intersection. So this is at 100 of the population. That is at years 5.372. Okay. Once again, you can just find this all out by plugging into the function. Plugging the 100 would go here. You'd multiply that bit over and solve for x. The final thing is to look at what is the limiting population. Okay, here is the population function, and we're asking what is the limiting population? In other words, if x goes to infinity, what does the population go to? So let's think about this using this function here. We're asking what happens when x gets larger and larger and larger? Well, if x gets larger and larger and larger, this number here becomes more and more negative. So think of this thing as its own function. So e to the power of negative 0.462. If you were to graph that, you're going to see it's going to look something like this. Yeah, so it looks like this function goes to 0. It asymptotes to 0. And so as x gets larger and larger and larger, this thing just gets closer and closer to 0. And as x goes to infinity, e to the negative 0.462x goes to 0. So this thing we can just say is 0. Well, if you plug 0 in for that, you can see 0 times 54.8 is just 0. And we get 1 plus 0 is 1. That means this thing just equals 558 wolves. That's the population as x goes off to infinity. That's the limiting population. We can see that on the graph by this guy here. This is flatlining. You can see that it's getting higher and higher. And there it says 558. That's just because it's so close to 558 that it just rounds to 558.